We've been looking at physical models which focus on the production of sound. Now we're going to turn to what might be called spectral models, which focus on the sound that actually arrives at the listener, and often described in terms of spectrum because that's what our perception is so sensitive to. I'm going to talk about some work that I've done with a number of colleagues over many years. This is called spectral interpolation synthesis. To begin with, let's think about additive synthesis and table lookup synthesis. So in additive synthesis, every partial has independent frequency and amplitude control. And it's possible to do analysis of sounds from acoustic instruments and to resynthesize those, but it's very difficult to get real parametric control over additive synthesis. There are a huge number of parameters, and so doing something as simple as stretching the note or adding vibrato means that you have to go in and somehow recompute all of these parameters that you've analyzed, and it's a difficult problem. On the other hand, table lookup synthesis has the relative amplitudes of all partials locked in because they're all combined into one waveform stored in a table. Therefore, all the frequencies are harmonic. The control parameters are much smaller and a little simpler to deal with, but the resulting sound is just not so rich because the spectrum is frozen. Let's review what goes on inside of a table lookup oscillator. This is some C code, which you don't have to understand in detail, but let's just go through some high points. First of all, there's a wavetable that here has a length of 512. There's one extra sample at the end, so the array is declared to be of size 513. The last sample is just a copy of the first sample, and it's there so that we can do interpolation without checking for wrapping. We'll see that below. Now, we go through a loop to compute samples from this. And inside the loop, we do two things. First of all, we do a table lookup, as you would expect. And secondly, we increment the phase. So in the table lookup here, we first round the phase down to the nearest integer. We call that I phase. And we do a table lookup, table of I phase. The next line here, which is actually most of the work, is doing a second lookup at I phase plus 1 and doing a linear interpolation based on the fractional part of the phase. The phase increment is simply adding an increment value to the phase, which I'll remind you is a floating point number. And if the phase goes over 512, then we subtract 512 to wrap around back to the beginning of the table. Now, spectral interpolation is simply interpolation between spectra or interpolation between tables. If you want to do interpolation between tables, which is very efficient, then it's important to keep the phases coherent between the two tables so that when you interpolate from one table to the next, the phases are lined up and you don't get any phase cancellation. So the computation looks like this picture down at the bottom. We compute the phase once, but we do two table lookups, and then we interpolate the result. And this method is restricted to generating harmonic spectra, but as you can see, by putting different spectra into different tables, we can get spectral change over time just by changing the relative weights on table 1 and table 2. Now, two tables might not be very interesting, but imagine if we could change the spectrum continuously over time into almost any harmonic spectrum we wanted. And we can do that simply by reloading the tables as we're doing the computation. So the way this works is we put the initial spectrum in table 1, we start generating sound, and we put a new spectrum, that you could call it the target spectrum, into table 2, and we interpolate from the current spectrum to the target spectrum. When we reach the target spectrum, in other words, the weight on the target is 1 and the weight on the initial table is 0, then we can form a new target and put that spectrum into table 1, and then we interpolate back from table 2 to table 1. And we can continue going back and forth from table to table at a relatively slow update rate of maybe 20 tables per second. We can generate very smooth, continuous spectral transformations. So where do these tables come from? Well, here's the more complete picture of spectral interpolation synthesis. We pull the tables, the wave tables, from a two-dimensional grid of wave tables, and this grid is indexed by the current frequency and the current amplitude, so that as an instrument gets louder, the spectrum changes. As the instrument changes frequency, the spectrum changes. And we typically interpolate among tables within this grid to form the next or the target spectrum. And then we compute a wavetable from that, store it into one of these two wavetables, and interpolate between them with this interpolation control here. So then the question might be, how do we find the spectra that we load into this grid of tables? Well, what I've done, and with my colleagues, is we use a phase vocoder style analysis to analyze the strength of each harmonic in a sound. And for the sound, we do a crescendo at different pitches. So you'll hear some trumpet examples later. And what I did was I played trumpet starting very soft, getting louder and louder on each pitch. And that gives us samples at every pitch and every loudness or dynamic level. And from that, we build this two-dimensional table or grid. Now, one of the problems with spectral interpolation synthesis is while we're able to reproduce harmonic spectra quite well, and even have those spectra vary over time according to the ways that we hear in actual acoustic instruments, there is a problem with attacks on many instruments. So the attacks or the note onsets are rapid and often inharmonic, particularly in brass instruments. Also, some woodwinds, the saxophone is a good example. They have very fast attacks, and these transitions don't really settle down into a periodic harmonic waveform until 10 to 30 milliseconds. That initial transition period, even though it's very short, is very salient to our ears. We really get a good impression of what is producing that sound just from the first 10 or 20 milliseconds. So we've got to get that right. And our solution, after trying lots of things, is very simple. We just sample the attacks. And then the problem is, how do you take a sampled attack and splice it cleanly onto a synthesized steady state portion of the sound? Well, you might think, oh, we'll just crossfade and it'll be smooth and no artifacts, it'll be great. Crossfading does not work. The reason it doesn't work is that even though the transition is smooth and continuous, some of the partials that you synthesize will have different phases from the partials within the sampled attack. And so the phase cancellation or effectively phase shifting happening over a small time interval, especially during that attack portion that we're so sensitive to, results in problems and distortions, and it just doesn't sound natural. What we do instead is more complicated, but it's necessary to make this scheme work. We analyze the phase of every partial at the end of the attack, after the attack sort of moves into a more periodic steady state phase. And then we synthesize tables with a phase that exactly matches the measured phase. And then, just to eliminate any tiny phase discrepancies or amplitude discrepancies, we do a very short crossfade. So we've seen how to build a synthesis model that can deliver continuously varying spectra at very low computational cost. It can deliver inharmonic attack transients that are very realistic. And we've seen how we can populate this model with spectra measured from real acoustic instrument performances. So this might be a good time to take a break and think about that part of the model, make sure you understand it. And when you're ready to move on, come back to the video and we'll get started. The next problem we want to talk about is, where does control information come from? We've seen how to provide spectra and attacks and other information to the synthesis model, but what remains is how to change the frequency and amplitude controls that are used to select the spectra. In traditional synthesis research, the way people historically approached the problem is to design synthesis algorithms. So we've seen table lookup algorithms, we've seen FM synthesis, and so on. And the idea has always been that if you could just come up with the right algorithm that produced the right spectra, then you could figure out how to control it and you could make good sounds. So the tradition has been to build a synthesis algorithm, make some sound, take a performance of a real acoustic instrument, make some sound, and compare them. So the focus, once again, is on the synthesis algorithm. In spectral interpolation synthesis, we take a little bit different approach. We're not satisfied with just the synthesis algorithm. We want to produce both control and synthesis. We do this through a divide and conquer approach. The first step is we apply a performance model to a score in order to generate control signals. And then secondly, given the control signals, we apply a synthesis model to produce audio. So we really have two models, the performance model and the synthesis model. In keeping with this divide and conquer model, let's look at the synthesis model first. The way that we build a synthesis model and refine it is we start with a score. We have humans perform the score because we don't have a performance model yet. And we take the audio from the human performance, and that's going to be the reference that we listen to. And then we extract parameters from the audio. And in the spectral interpolation synthesis model, the main parameters are frequency and amplitude envelopes. These are relatively easy to extract, but I'll tell you, in practice, performers make glitches. Little things happen, like the trumpet valve will go down a little after the attack, and something comes out that's not a clean signal that fits within the model very well. And so usually the data requires some cleanup. But in any case, we can get realistic amplitude and frequency contours as control signals. We put those into our synthesis model, our instrument model, and audio comes out, and we compare it to the original. If we don't like it, if we hear some problems, we can go back and refine the instrument model and resynthesize, and we can keep iterating on the model until we perfect it. Now that we have a good instrument model, the next thing we want to do is solve the control model or the performance model and refine it. And so the way we do that is, once again, we go back to the human performance, we extract parameters, and we have these control signals from which we can use our instrument model to produce audio. So then we build a performance model. So this is going to be something computational that can take the information in the score and produce frequency envelopes and amplitude envelopes that we hope will sound realistic when they are used to drive our instrument model, which we know is good because we did that on the previous slide and perfected it. Okay, so we listen to the results, compare the model driven by actual human control signals versus the instrument model driven by our computational performance model, and we can listen to the differences, try to update our performance model to perform better, and again, we iterate until we've refined the model. I'd like to make some of these ideas more concrete by looking at some real envelopes of trumpet performance and talk about a study that we did analyzing trumpet envelopes. First of all, envelopes are crucial to sound synthesis. And what we discovered is that the shape of the envelope depends critically on musical context. In a lot of prior work, people spent time analyzing envelopes of different instruments, but always with isolated tones. And the idea was that you could analyze isolated tones, figure out how to make a good sounding violin note or trumpet note or something, and then you could string these together and make melodies and phrases and music that sounded like a violin or a trumpet. It turns out that this just doesn't work. This is not how instruments work. And it's important to know that if you're working on sound synthesis. So we claim that envelopes are largely determined by context, and that good envelope generation techniques can vastly improve sound synthesis. So here's the big picture. We have in spectral interpolation synthesis a score to begin with. We take that score and we produce envelopes, control signals that might look like this, and then we synthesize using our spectral interpolation instrument model to make sound. There's a lot of related work talking about envelopes and expression and how to make musically shaped envelopes. And the key to all of this is you have to consider context and study envelopes within musical phrases. We did an experiment with the trumpet where I played the same note, same duration, sometimes different dynamics in a different context. So you can see, for example, context 1 is we're going up a chromatic scale. Context 2 is we go down a half step and up a half step. Context 3 is we change the dynamics. Context 4 is we do the same descending line but using a slur. We do the same line using large intervals, and so on. And the question is, how do these different contexts affect the center of mass of the envelope? And so why are we asking about center of mass? Well, if you wanted to characterize a shape with one parameter, that might be a good way to do it. It's just an attribute derived from the overall shape. And what did we measure? We measured envelopes from onset to onset. So in other words, the inter-onset times define the duration of the envelope because we think these times are the most repeatable and well-defined. Here are some data at the bottom. These are envelopes from one context and from a second context. And so you see that given a fixed context, the envelopes are quite repeatable. As you might expect, they were all performed at the same session by the same performer. But clearly these two shapes are overall different. So that means that context is in fact affecting the shape of the envelope. So some results that we obtained are, first of all, phrases where the pitch goes up and then up again show a later center of mass than other combinations. Large intervals had earlier centers of mass than small intervals of pitch. And if you articulate with a legato style, so in other words, long notes as opposed to short notes, then you have a later center of mass than otherwise. And this should be obvious. If you're sustaining the note for a longer period of time, then the envelope is not going to decay as fast, and so the center of mass would naturally be later. So let's go back now to spectral interpolation synthesis and think about what all this means. Here is a typical example of the envelope of a tongued note on the trumpet. Tongued means that the note is articulated by stopping the air with the tongue and then releasing the air at the beginning of each note. So it's sort of like playing ta, 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 and I can demonstrate that on a real trumpet. The envelope can be thought of as having two factors working together. One is the breath, which is this overall shape here, which I believe is the result of large upper body muscles from your diaphragm and chest, creating air pressure. And then there are some fast acting onsets here and offsets here, which I believe are the result of the tongue, which is able to move much more quickly. And that's why we use the tongue to articulate notes. In contrast, here's an envelope of a slurred note. So let me play some slurred notes. So you hear it sounds much more continuous because the tongue is not used at all. We're just blowing air more or less constantly and changing the pitch with the lips and the valves. And here we can see that this is also modeled with the breath envelope, and some kind of transients happen here due to the valves changing the tubing. In our model of envelopes, the breath envelope gives the overall shape and the tongue articulates the beginning and the ending. We developed a parametric description in these terms where we, first of all, take a sort of general envelope shape like this, and we specify where we're going to start in the envelope and where we finish. So that gives us actually, these two parameters give us a lot of control over the overall breath shape. And then, of course, we scale the duration to be the appropriate duration. And then we have a bunch of other little parameters for describing these typical shape of the onset and offset. That slide had 9 detailed parameters, and we compute these parameters from pitch, duration, whether or not we are at the beginning of a phrase or the ending of a phrase, whether we are coming from a slur or the note is slurred to the next note, and also whether the pitch direction is up or down. The score provides these actual parameters, and we study real performances to derive envelopes. And in our first work, we actually found these detailed parameters for these envelopes manually. And then, given the parameters and a lot of data, we looked at it and looked for trends. And we tried to generalize these observed trends to come up with some rules for designing envelopes. For example, here's one rule that was encoded in Lisp. We said if we're coming from a slur, then this TF parameter, written here as take from, is either 0.1 or 0.04, depending on whether or not the direction, in other words, the pitch change, was up. And then there's another case, if we're not coming from a slur, then the take from parameter is this expression involving the logarithm of the duration and some other factors. Okay, here's a table describing how this take from parameter depends on whether or not we're coming from a slur and whether the pitch direction is up or not. The details of this don't matter. The important thing is the method is that we look at the context and we write some equations for each context to describe each parameter. Here's some more. I'm not going to go through this in detail. Same idea. This is how we get envelopes from the score. We have a number of parameters. We also have a reference breath envelope, which is a given envelope, and we crop it and stretch it using 3 parameters. Then we multiply the breath envelope by attack and decay envelopes that are controlled by these other parameters. And all of the parameters depend on pitch, pitch context, articulation, the next note articulation, and the duration. In our initial work, this was a handcrafted mapping. It took a lot of time, but it produced some pretty good results. For the frequency envelope, we didn't do nearly as much work. We used analyzed frequency envelopes from trumpet performances, which capture the natural frequency variation of the trumpet, which is not purely steady. Maybe if you listen carefully, you'll hear some pitch variation. Not too bad, but not perfectly steady. And the frequency envelopes are pitch dependent. We did not model vibrato. Here are some sound examples. So that was a synthesized trumpet. That was also a sample-based synthesized piano. Here's another example. In this example, the trills were a little bit of a problem. They fell outside of our normal model, and we probably played them a little slow. And one final example. So that's a pretty natural sounding trumpet performance, and that is completely synthesized from the score. So there's no hand tuning of the envelopes for this particular performance. So in summary, we can model a synthesis method on real performance. We do the computation a phrase at a time so that we incorporate the context of notes. We use melodic direction, articulation, duration, pitch, and all in order to compute appropriate envelopes. And currently, well, at least in the work that you saw, everything was rule-based and more or less ad hoc. And our conclusion is that envelopes are critical to music synthesis. Statistically valid relationships between score parameter and the envelope shape can be discovered and used for constructing envelopes. We created this model of the breath plus tongue to explain and model and compute envelopes for trumpet. And I believe that the study of musical phrases and notes in context is critical to future synthesis research. We can go further and talk about the implications of this work for synthesis in general. Based on these examples and others, I claim that we have an adequate synthesis algorithm, at least for trumpet. And what happens if we return to the traditional synthesis research model with the spectral interpolation synthesis algorithm? Well, remember, the traditional synthesis research looks like this. And if we perform our synthesis model with standard envelopes, as you would do in the traditional synthesis approach, you would get something like this. So to me, that sounds really terrible. It sounds like a cheap synthesizer. It doesn't really sound like a natural trumpet. And yet, that is exactly the same synthesis algorithm that produced this sound. So the only difference is the control information. So since the only wrong ingredient is the envelope shape must be critical for synthesis and for our identification of instruments. This observation could only be made after we perfected, or at least came pretty close to a good trumpet synthesizer. And so it follows that previous work on synthesis was wrongly assuming that simple envelope templates are sufficient, because this is traditionally how people studied algorithms. In other words, in the past, if someone had come up with a good synthesis algorithm, how would they even know? They never would have heard the full potential of that synthesis algorithm because they weren't using good control functions. This is one argument, I believe, against physical models in that line of research, which is that they're so focused on the synthesis algorithm and not thinking about control, that even if you had a great physical model, you might not know it. And the physical models do not really give you a method like we have to construct envelopes and control signals. Remember that we had a divide and conquer approach with a systematic way of obtaining envelopes and envelope models. So just to give equal time, though, I talked about this with Julius Smith, who is very well known for his work with physical models. And Julius's answer, I think, was a great one. He said, basically, my goal is to develop sufficiently rich instruments that musicians will want to learn how to control them. So he at least is not claiming that he has solved the control problem, and he thinks that perhaps the control problem is really one of delegating the control to human musicians performing synthetic instruments in real time.